Hi, I am Mayaritza Barrales Romero, and this is the fourth activity about saponification process productions with our partner CMX about this challenge. This project aims to design and optimize a chemical reactor for the production of a fat complex enrichment with cellulose and calcium soaps, engaging yield and process efficiency. This study focuses on the reactor selection, operation conditions, temperature control, and to evaluate the effect of the reaction rate, the conversation, and sustainability, minimizing the energy consumption and the environmental impact. About CMX, the product enhances ruminant like milk quality through omega fatty acids, but highly lectin levels about less than 28%, causing mixing and stability issues about 35 degrees Celsius. CMX addresses this using a double charge mixer and 3% of ClCl2 to convert omegas into stable calcium soaps. Current yield is 74%, but optimizing temperatures and mixing conditions could increasing up to 95%, reducing cost and improving competitiveness. For the experimental system, we present these two reactions. This was were modeled the saponification of the triglycerides with sodium hydroxide to form soap and glycerin, followed by a precipitation of the soap as a stable, non-soluble calcium salt, ideal for animal feed. To evaluate the kinetics, we do a batch reactor operate at 30 or 45 degrees Celsius was used. Samples were titrated with hydrochloric acid and phenolphthalein to determine the NeoH concentration and thus the conversion of the reaction. So we have this plot. So the results shows that sodium hydroxide consumption decreased with time, confirming the progression of the saponifications, and a 45 degrees the reaction accelerates, validating the on overall second order kinetics and pseudo first order behavior in excess of NeoH. Molar mathematical modeling and balances is we do molar and energy balances that were developed for a non-adiabatic serial liquid reactor, considering heat transfer to the jacket that we use. This is simulated in polymath to allow to be simulations of the conversion of the thermal profile over time. We choose a batch reactor with a jacket, so it's a non-adiabatic. Allowed to simulate, and this polymath allow us to simulate both adiabatics and heat loss systems to just adjusting the global parameter UA.
This
All
thermodynamic
these
parameters
thermodynamic
and this
parameters and
validation
this
and this
validation
validation
is
is
because
because
the
all of
thermodynamic
this data
data
for
for
each
each
piece
piece
was
we
taken
taken
from
from
NIST.
NIST.
The
The
reaction
reaction
exhibited
excited
at
a
a
heat
heat
of
of
reaction
reaction
of
of
minus
252 kilojoules by mole,
252
confirming this is
kilojoules by mole,
exothermic nature.
confirming
So
its
simulation
exothermic
predict
nature.
a moderate
The
temperature
simulation
increase
predicts
about 20
moderate
during
temperature increase to
operation.
about 20
This
kilo
thermodynamic parameters
during
and
this
this validation.
operation and this validation. For our computer model, we'd use like a polymath code. So this is our code, and this is the results that we have. Like I said, based on the evaluation and the experimental result that we do after, the proposed design can increase the yield up to 95%, reducing oxidation loss and improving product stability and its scalability to a semi-continuous reactor and feasible for a large-scale reactor production. I'm sorry. In conclusion, this reactor, we have like optimization of saponification and calcium formations. We validate thermodynamic and kinetic modeling, and it's an efficient and sustainable reactor. The reactor designs allow us for integration of the principles of kinetics and thermodynamics and simulations to improve process efficiently, and this approach lays the foundation for the sustainable production of the omega and ceolite enriched nutritional additives. So thank you so much for seeing the video.